Welcome everyone to what is the fourth of our virtual technical meetings for the IMAPS New England chapter. I will momentarily pass it over to our chapter president for some brief announcements before we go to our speaker. Just some logistics. I think at this, by this point, everyone should be pretty familiar with WebEx, but I want to point out that you could, what's proved most effective for questions is the chat space. So that would probably be the best thing to use, and then we'll go through them when our speaker is finished. So let me pass it over for temporarily to our chapter president, Matt Bracey.
Thanks, Richard. Welcome, everybody. Thanks for joining us this evening. It's great to have you. We have an exciting talk ahead of us from Michaela. I look forward to that. And just a couple quick announcements to make. Next month, February 18th, will be our third symposium session. It's the RF session B. It's our second RF session. And it should be a great session. We have 4 good speakers on that, and I'm going to post a link to the chat box where you can register for that if you're interested. And then the other announcement I have to make is we have a tentative date for March 16th for our next chapter meeting. So that's tentative. We have more details coming out, but we're still working on that. But we'll get that to you as soon as we can. Other than that, sit back and enjoy the meeting tonight. Thanks, guys. Back to you, Richard.
Okay, thanks, Matt. So for tonight, our speaker is Michaela Connell, and Michaela joined FUJIFILM Electronic Materials in 2017 after graduating from University of Rhode Island with bachelor's degrees in chemical engineering and French. Is that right?
Yeah.
Oh, impressive. So she is an engineer at FUJIFILM in the New Business Development Group, and has taken over as project leader for their dry film applications. So, I would prevail on everyone who is not muted to mute themselves so that we can all hear the speakers. And I will now pass over to Michaela.
Thanks, Richard. All right. Hi, everyone. As Richard said, I'm Michaela Connell, and let me start sharing this presentation with you. All right. Can everyone see my screen?
Yes.
Okay, great. All right, so today I'll be presenting on rheological considerations in characterization of organic dielectric films for advanced packaging applications. Myself, along with my colleague Stephanie Dielocker, are the contributors to this paper. So today I'll be going over the kind of basics of our polyimide dry film packaging, advanced packaging challenges, examples of pore filling and planarization, our results, rheological properties, the effect on thermal properties post-cure, and effects on other film properties. So our polyimide dry film is packaged in 3 layers. The polyimide dry film is coated onto PET carrier film and then covered with a BOP cover layer, which is removed before lamination. The polyimide dry film varies in thickness and is typically coated to be about 5 to 40 micron thick. And in advanced packaging, we're relying more and more on multi-layer RDLs and embedded chip packages. So planarization is important as form factor is becoming thinner and complexity of topography increases. Complete via filling of dielectric material is also important for electrical integrity. So in this presentation, we will investigate if the use of polyimide in the form of dry film helps to alleviate the challenges of planarization and filling in advanced packages. So here we have an example of a typical polyimide dry film laminated at 120 degrees Celsius. As you can see, even at 120 degrees Celsius, good filling and planarization could not be achieved, presumably due to high melt viscosity of polyimide dry film. On the left, we have an embedded chip with a 100 micron deep and 25 to 30 micron wide cavity between the chip and the substrate. And 12 micron dry film, even when laminated at 120 degrees Celsius, we were unable to create enough flow to even achieve 10% of filling. And on the right, we have topography with a height of 2.5 micron. And even with 12 micron film, the dishing between the structures is 1.6 micron. In order to create flow with this polyimide dry film, it may be necessary to increase the lamination temperature even further. However, temperatures greater than 120 degrees Celsius are not feasible in this case due to melting issues of the carrier PET film. And in this example, you can see that on the left, the same embedded chip structure that we saw in the previous slide has been successfully filled and planarized. And on the right, you can see that the dishing has been reduced to 0.8 micron between the 2.5 micron high topography. And these were achieved at a lamination temperature of 90 degrees Celsius. So how did we achieve this? So we adjusted the rheological properties of the polyimide dry film by using a combination of reactive and non-reactive diluents, which act as effective plasticizers. When we plasticized the film, we were successful in creating good flow at lower lamination temperatures. However, there are important considerations when altering the rheological properties that also needed to be studied. So when we were looking for additives which would successfully alter the rheological properties, we also had to consider other important factors. One of those being the compatibility with our existing polymer and other formulation components. And another is when we added these diluents, was it going to meet our filling and planarization needs? So in this case, we looked at storage modulus and loss modulus in order to determine if this would have effective rheological properties for filling and planarization. And then we also had to look at the effect on the film properties. What is the role of the unreacted diluent, and what is the role of any residual inert diluent? What effects will these have on our mechanical properties, on our lithographic properties? So these are all things we considered when studying different diluents. So several reactive and inert diluents were tested to study the impact of flow properties by dynamic mechanical analysis. We selected this combination of diluents, which systematically lowered the storage modulus. As you see in this figure, we added two different levels of diluents, which decreased storage modulus as the amount increased. So here we have the first level of plasticizer of the diluents, and then we have the second level, which is higher, and both have systematically lowered the storage modulus. So lowering the storage modulus and loss modulus also resulted in lowering the melt viscosity of the polyimide dry film. Low melt viscosity and low modulus are important to ensure good flow and filling. Based on these results, it is clear that we were successfully able to favorably alter the rheological properties of this application. However, as I mentioned previously, we must also look at the impact of altering the rheological properties on the other properties of the film. Such low storage modulus is unacceptable for the mechanical integrity of the film. So we then looked at the impact on the cured dry film of adding these diluents. In this figure, you can see that the difference in the thermal properties between the cured and uncured plasticized films. When we look at the TG of the cured plasticized film, the TG is 230 degrees Celsius, which is almost identical to TG of the unplasticized film, which was measured at 232 degrees Celsius. And then when we're looking at the TGA results, there is no difference in the weight loss between the unplasticized and plasticized cured films, indicating that no residual diluent is remaining after curing at 170 degrees Celsius for 2 hours. This result shows that there is no impact of plasticizer on the thermal properties of the cured polyimide. Okay, so now let's look at the other possible effects on the film. So here we have the stress strain curves, which post-cure have nearly identical results. So on the left, we have the unplasticized polyimide dry film. On the right, we have the plasticized. And the elongation to break, UTS, modulus, and tensile stress at yield were all extremely close, nearly identical, meaning that the diluents have no effect on the mechanical properties post-cure. So next we have reliability studies. Here we performed a 96-hour unbiased HOST at 130 degrees Celsius with 85% relative humidity. The films were laminated on an RDL patterned silicon oxide wafer with 10 micron line space and 6 micron copper structures. This was laminated with approximately 10.5 micron dry film. The unplasticized dry film was laminated at 120 degrees Celsius, and the plasticized dry film was laminated at 90 degrees Celsius. Both were blanket exposed at 500 millijoules in eye-line and cured at 170 degrees Celsius for 2 hours in the S7. As you can see in the images, there was no effect of the plasticizer on the reliability of the film. Both had identical results. So next, this is the imaging performance. As you can see, the ultimate resolution was identical in the focus exposure matrix, and both the plasticized and unplasticized films show a 2-to-1 aspect ratio at the best doses and focuses. Chemical resistance was also performed on both plasticized and unplasticized films with both patterned and flood exposed films after 170 degrees Celsius for 2 hours cure. We used 5 different chemistries. We used RTS4, which is a commercial photoresist stripper based on DMSO, NMP, and a proprietary amine. We also used 2% HF, 10% sulfuric acid, 2.38% TMAH, and 10% KOH. These were done for 30 minutes at room temperature besides the RTS4, which was done at 30 minutes at 55 degrees Celsius. And in this case, we defined passing by a film thickness change of less than 0.5% and no cracking or discoloration or lifting of the films. By this criteria, both films passed when both patterned and flood exposed, showing that the plasticizer had no effect on the chemical resistance of the film. So in conclusion, typically high melt viscosity dry film cannot successfully fill and planarize challenging topography, even when laminated at high temperatures. Using a combination of reactive and non-reactive diluents, which act as a plasticizer, we were able to successfully alter the rheological properties in order to fill and planarize 100 micron deep cavities, as well as planarize 2.5 micron high topography at lower lamination temperatures. Post-cure, there was no weight change between the controlled dry film and the plasticized dry film, indicating that there is no unreacted diluent left in the film post-cure. And the diluent had no effect on the post-cure properties or the imaging performance of the polyimide dry film. Thank you. Does anyone have any questions?
Okay, if anyone who has questions, I think if as long as we don't have a lot at the same time, it would be okay to just unmute yourself and speak up or use the chat room. So I think those results were very impressive, and I hope I get a chance to do some processing on that material.
Yeah.
Hi, can you hear me?
Yes.
Hi, this is Alexa Lipschitz from DuPont. A very nice talk. I was wondering about, any type of performance that you've looked at in terms of metallization of this material and ability to, show similar adhesion properties to other kinds of PI materials out there.
Yeah, so we actually did some shear tests with both the unplasticized and plasticized dry films, and they had identical adhesion, at least by shear test, on copper, silicon, and EMC. In terms of the comparison to other polyimide dry films, I'm not sure, but at least compared to ours, without the plasticizer, they were identical.
Got it. So it doesn't interfere. Thanks very much. A very nice talk.
Thank you.
Hi, Michaela. This is Rajiv from Medtronic. I had a quick question about mechanical testing on thin films. What kind of systems do you use for doing some kind of like shear test? And is it like a lab shear, or is it a different kind of shear test that you guys do? I was just curious in understanding the challenges behind mechanical testing. Because when I was working for Instron, that was one of the things that we had a real big problems about. Thin film testing there.
Yeah, so for shear test, we use a Zytek tool. It also has peel testing capabilities depending on the stylus you use. But we use 100 micron stylus and 200 micron stylus to test the shear test properties. Let me see. I don't know if that answered your question, but yeah, we use a Zytek tool for.
Yeah, I mean, I guess I was just curious to kind of understand more about the system, but yeah, I mean, I get the magnitude of the dimension of stylus that you use for doing the shear test.
Yeah, so we create pads on a wafer with our desired substrate. So we'll coat or laminate on a 4-inch copper, silicon, or EMC wafer, or whatever substrate. And we typically go for 12 micron film, and then we use the Zytec. I'm trying to see if I can find the force that we typically use.
Okay. Yep. Thank you.
No problem.
Okay. Doesn't look like we have any more questions coming up. So I'd like to thank our speaker for a very interesting talk.
Thanks,
And,
everyone.
oh, look at that.
Oh, you can send applause.
I didn't know that icon was there. There you go. That's good. All right. Well, thank you very much. And thanks to everyone for joining us. And I hope to see you back in March.
All right.
Thanks for having us, everybody. Appreciate it.
Thanks, everyone.
Thank you, Michaela. Thank you, Richard.
Thanks.
Thank you, Michaela.
Thanks.